So today what we're going to be looking at is more applications of some of the stuff we've said about derivatives to the natural and social sciences, different things, also financial mathematics. In particular, I want to look at why exponential functions show up so often all over the place. And so that is going to sort of occupy most of what we talk about today. Here is the thing about exponential functions, okay? And I mentioned this last time, but we may as well go through it again. If we look at the function ae to the kt, then this has the property that f prime of t is equal to k ae to the kt, which is actually just k times f of t. In other words, functions of this form, their derivative is proportional to the function itself. Now, it turns out, as we will see soon, these are the only functions with this property. So any function that has a derivative which is proportional to itself has to be one of these types of functions. It's not yet obvious, though, that these are the only functions with this property, but we can see they do have this property. So what this means in particular is that if I have y prime equals ae to the kt, then if y is equal to ae to the kt, then y prime is equal to k times y. Now, why does this matter so much? Well, because there are a lot of situations in which this kind of equation is expected to be obeyed. In other words, what we're really looking at here is the rate of change of y is proportional to y itself. Why is this camera having so many issues focusing today? I don't know what is up with that. I wonder if I open this up a bit, if that will fix it somewhat. There we go. There, that's much better. Okay. Hopefully that makes it easier for you to see this board. So, this kind of situation, this kind of equation is one that shows up all over the place. And an equation like this, and this is getting a bit beyond what we're going to really focus on in this class, but this is known as a differential equation. What is a differential equation? Well, a differential equation is an equation where instead of just having a variable in it, where the variable represents a number, we have a function in it, or a variable that represents a function, and we also have derivatives of that unknown function show up. And our question is, what functions will satisfy this equation? Well, what we can see just by checking is that this will solve this differential equation. What's not yet obvious is why this is the only solution, or the only family of solutions that we can get. You'll notice, by the way, that A here is arbitrary. In other words, it doesn't matter what value of A I pick here, it will still satisfy this equation. So, we don't have to worry about that. Now, what we would like to do here is take a look at some places where this kind of equation shows up in the real world. And I'm going to start with some from physics, because physics happens to be something that, I was a physics major as an undergraduate as well as a math major, so it happens to be something I'm more or less familiar with. We'll start from there. Your personal interest may be slightly different, and that's perfectly fine, okay? We're going to get to all kinds of different applications, but we got to start somewhere. I'm going to do physics. So, in physics, in nuclear physics, for example, we have nuclear decay. And nuclear decay, well, actually, nuclear decay is an interesting one because it's not exactly what I wrote down in that previous example. Or rather, we don't usually write it quite that way. So normally what we say is that if I have some amount of nuclear material or radioactive material, then this amount satisfies the equation. The rate at which the amount is changing is equal to negative k times the amount. And the only difference here is that we've got this negative. Well, what are the solutions? This is going to be A of t is equal to A0 e to the minus kt. And again, it's not hard to check that this really does solve this equation. It really satisfies it. Okay, so I'll let you check to see that that is actually true, but it's very straightforward. So what does this mean? What is this really saying? Well, this k here is known as the decay rate. It is the rate at which this given material decays. And the decay rate is different for different materials. And what that decay rate is depends upon all kinds of factors. So generally speaking, sometimes we can calculate what the decay rate ought to be theoretically. Sometimes we just kind of measure the decay rate. Usually we got to measure it to make sure that our theory is correct anyway. In fact, that was one of the things I did as an undergraduate, was an experiment involving measuring decay rates of a certain kind of substance known as orthopositronium, which for some reason the measured decay rate wasn't the same as what we were predicting it should be, and we were trying to figure out what was going wrong. It turned out that the reason people were getting the wrong answer is because they were not doing their experiments quite correctly. But anyway, the decay rate simply refers to the rate at which something is decaying, and it is generally going to be in a proportion. So this proportion decays over a given time period. And then t is the time that has transpired. And what is A0? What is this constant? Well, to figure out what that constant is, notice that the amount when t is equal to 0 is A0 e to the minus k times 0. Sorry, that doesn't look much like a multiplication symbol. But this is e to the 0, which is 1, which is just A0. So actually, A0 is the amount at t equals 0. So that is our question here. Or that is our constant here. On the one hand, mathematically, it's arbitrary. Any value of this constant, we will still satisfy this equation. But in terms of the applied problem, it is not at all arbitrary. It's going to depend on how much do we start with. So as an example of just really quickly setting up one of these equations, maybe we say that a certain material decays at 1 part in 10 per year. And if we start with 12 kilograms, write a function for the amount after t years. Okay, well, the answer to this is just going to be A of t is equal to our initial amount of 12 kilograms times e to the minus 1 over 10 times t. And this is going to be in kilograms because that's what we're measuring this in. So setting up this equation is pretty straightforward. But usually we're not just going to be asked to set up the equation. Usually we will be asked to solve some further question involving this thing. So we could go on to say, okay, maybe we're working the same type of problem, but what if I then ask you, when will we have 1 kilogram remaining. Now, this is a kind of question that's very relevant in a lot of situations. Because, for instance, let's say that we have a nuclear material and we're done with it, we want to safely store it. We need to know when is the amount of radioactive material going to be down to a level that is safe to approach. We want to keep it back behind lead or in some other kind of radioactivity proof substance. We need to keep it sealed up for a certain amount of time. When is there going to be a low enough amount that we can say, okay, it's no longer dangerous, we don't have to worry about it? 1 kilogram still probably is dangerous. So this is not like, you wouldn't normally say, oh, it's fine, we'll just toss a kilo of radioactive material around. No, that's probably not what you're going to do. But it's the same kind of principle here. So the way that we're going to solve this then is we're going to say, well, what we want is for 1 to be equal to a of t, which is 12e to the minus 1 over 10 times t. And I'm just going to solve for t. How do I go about solving for t? Well, I can isolate the exponential and say, okay, so this means 1/12 equals e to the minus 1 over 10t. And then I can take the natural log on both sides. So I can say the natural log of 1/12 is equal to minus 1 over 10t. Now this is actually negative log of 12 equals negative 1 over 10t. So this gives me t is equal to 10 times the natural log of 12. And I got this negative thing because remember 1 over 12 is 12 to the minus 1. But then I can bring that exponent out front of the natural logarithm. So that's where that negative came from. So after this many years, we will be down to 1 kilo of radioactive material. I don't know how long this many years is going to be, but we can, throw this into a whatchamacallit? A calculator. That is the word I'm looking for. Calculator. We can throw this into a calculator if we want a decimal approximation. So there we go. Now, another type of question that we might ask, and this is one that comes up a lot in archaeology and biology and things like this. This has to do with measuring the age of an item. So how does measuring the age of an item work? You've probably heard of carbon-14 dating. Carbon-14 dating is not the only kind of radioactive dating, by the way. There are other methods that are used too. But carbon-14 dating seems to be the one that is most familiar to most people in the popular mind for some reason. Here's the idea. Suppose that you have some substance that you can estimate how much should be in an item when it was made. An example of this would be if I have, say, the body of an animal, then we know that animals contain a certain amount of carbon-14 while they're alive. Now, the problem here is that the exact amount of carbon-14, we can't pin that down. There's like a big range, okay? But there's a range of carbon-14 that you expect to find in a living animal. And so we can say, okay, when this animal died, it probably had such and such an amount of C14. And then we measure how much C14 you have today. And what we know is from the decay rate, we can then calculate how long it must have been to get from the original amount of carbon-14 to the amount of carbon-14 you have today. Now, I'm not going to work this problem with carbon-14. I'm going to work this with a slightly different sort of problem. So let's suppose that a substance has a decay rate of, let's say, 3 over 50 per year. And we want to say that if we started with 5 grams and now have 2 grams, how long has it been? So this is similar to the kinds of questions you ask when you do carbon-14 dating. With carbon-14 dating, you say, okay, we know the rate at which carbon-14 decays. We know at least approximately how much C14 the animal ought to have had when it died. If we can measure the amount of carbon-14 remaining, then we can ask how long would it take to get down to this level of carbon-14. Now, this is not necessarily going to be exact, again, because we don't necessarily know for sure exactly how much carbon-14 any particular animal should have had, right? It would be like saying, how much potassium should you find in a body? Well, it depends. We know that there's a range that ought to be there, but different people have different nutrient levels, different animals have different nutrient levels. There's all kinds of things that go into this. But let's leave all of those problems aside and just see how would you solve this. Well, the thing is that the amount that you have after a time t is going to be the initial amount times e to the minus 3 over 50 times t. So what we have now is that 2 grams is equal to, let's just write 2, we'll leave off the units for now, equals 5 grams times e to the minus 3 over 50t. Now, pause this for a moment and see if you can solve that and what you get. Okay, so did you figure it out? Solving this is pretty similar to what we did a moment ago in the previous example. We're going to say, first of all, we're going to say that we need more room and this whiteboard is abysmally small. Then we're going to say that 2/5 equals e to the minus 3t over 50. This means that the natural log of 2/5 is equal to negative 3 over 50 times t. But if I take the reciprocal here, this becomes negative log 5/2 equals negative 3 over 50t. So that means t is 50 over 3 times the log of 5/2. And again, you throw this into a calculator, the log of 5/2 is very close to 1. That's how long it must have been since we had 5 grams of this substance, if now we're down to 2 grams. So in this way, you can get a pretty reasonable estimate of the ages of things, at least as long as you have enough of the original radioactive substance left to measure fairly accurately. Now, this is where things get tricky because this is why carbon-14 dating only works up to a certain age. It turns out carbon-14 decays relatively quickly, and therefore, by relatively quickly, I mean like over a period of a few thousand years. It cuts down to about half of its original substance. So if we go back more than, like 100,000 years, it can be tricky to just use carbon-14 dating. We start to end up with just huge uncertainties there. So yeah, there's practical problems with using this method in some particular cases, but theoretically, the idea is very straightforward. Let's look at another concept involved here with decay problems, and this is what is known as the half-life. The half-life is usually written with the Greek letter lambda, which looks sort of like a Y that has been messed around with a bit, upside down and stuff. So the half-life, and by the way, no, we are not talking about the really excellent video game from the late 90s, which was still is one of my all-time favorite video games, but we are not talking about that. We are talking about something else, but this is where the name of the game came from, as well as the lambda symbol that shows up in the game all the time. It comes from this decay stuff, because remember, in the game you actually are playing, if you look at the backstory, you're playing a theoretical physicist who for some reason is working on experiments instead of theory. Anyway, what is the idea behind the half-life? Well, suppose that we have a decay rate of k, and what I want to know is how long does it take to have my original amount of whatever I have? Now you might say, well, that's going to depend upon how much you start with. It turns out it doesn't. And that's why this makes sense. So the half-life is going to literally be how long it takes to cut our amount of substance in half. Why doesn't it depend upon the amount that we started with? Well, look at what happens. What we have is a situation where A of t is equal to A evaluated at 0, e to the minus kt. Well, we're asking, when is A of t equal to 1/2 times A of 0? So this is the equation that I get. Notice it has an A of 0 on both sides. Well, that means this A of 0 drops out of the problem. It doesn't matter how much I start with. The answer is still going to be the same. And that's a really cool thing. So the amount of time it takes to cut the material in half doesn't depend on how much you started with. It cuts in half after the same period of time. You start with 10 grams, you start with 10 tons, it still cuts in half in the same amount of time. And what is that amount of time? Well, we're going to call that amount of time lambda. So let us solve for lambda here. This is going to give me the natural log of 1/2 equals negative k lambda. So this means that log 2 divided by k is equal to lambda. So there we go. There is this nice formula between the half-life, which is the amount of time it takes to cut something in half, and the decay rate. You can also write that the decay rate is equal to the natural log of 2 divided by the half-life. So we can go back and forth between these two concepts. As an example of this, we could say, well, given a half-life of, say, 6 years, write an equation for the material left after t years, starting with, let's say, 8 grams of the material. Well, the amount that I have left after t years is going to be 8 grams, and then it's going to be e to the minus natural log of 2 divided by 6 times t. And there we go. That's literally all we have to it. Notice, by the way, that there is kind of another way of thinking about the relationship between the half-life and this formula. Because if the half-life is the time that it takes to cut something in half, then, well, another way of thinking about the formula is that it should be the amount that I have left after t years should be equal to the amount that I start with, a sub 0, times 1/2 raised to the t divided by lambda. But notice that that is actually the same, and I'm going to leave this as a little exercise for you to think about here. Why is this the same as a0 e to the minus log 2 divided by lambda times t? Because these two formulas are actually identical. They are equal to each other. But you do have to remember a bit of stuff about the natural log function and about exponentials to see why this works. But sometimes I will say this formula that uses the 1/2 instead of the e, sometimes that formula can be somewhat nice to use. So you should be aware of its existence. Okay, now we've spent a bunch of time talking about this radioactive decay stuff. And the reason I spent a lot of time on this first one is because most of our other examples are going to go pretty much identically to it. So once you understand how one of these things works, you often end up seeing kind of like everything else sort of follows in the same way. So here's another example of something that we end up with using exponentials. Let's suppose that we want to talk about financial mathematics where we have continuously compounded interest. Well, continuously compounded interest has the property that the amount of money, which we're going to call P, the rate at which our money is changing should be equal to our interest rate times the amount of money that we have. Well, what this means is that the amount of money in our account is going to be equal to the initial amount of money, which is also called the principal investment, times e to the interest rate times t. And this is a very important formula for people who are interested in interest, financial mathematics, that sort of thing. It works pretty much identically to what we just said about decay. So we can ask exactly the same kinds of questions. Here's a sort of question that might be particularly relevant. So let me suppose that I want $1,200 in 5 years. I have $1,000 to invest. What interest rate do I need? Well, what we know is that the amount that I'm going to have after a time t is my $1,000 investment times e to the rt. But after 5 years, I want to make sure I've got $1,200. So I need $1,200 to be equal to 1,000 e to the r times 5. Make sure you understand where this equation came from and everything before you go on to the next step. Well, from here on, things become relatively straightforward. We just have to solve for r. So 1,200 over 1,000, that's 12 over 10, or 6 over 5, is equal to e to the 5r. That means log 6 over 5 is equal to 5r. So r is the log of 6 over 5 divided by 5. And from there, you can go ahead and you can say, okay, let's find out what that is in decimal, and then we can find it in percentages so that we can calculate what actual annual percent interest we need to have on our investment. Obviously, a higher interest rate would give us more than the 1,200, but this will tell us the minimum we need to just exactly hit that $1,200 in 5 years. Of course, really, you might want to consider investing in Dogecoin, but no, do not take financial advice from me. I am not a financial advisor. I try to stay away from financial mathematics as much as I can, to be perfectly honest. I do not find money particularly interesting. But this is an example of a problem that really is quite relevant, right? Like, if somebody's planning for their retirement, they might need to know this kind of thing. Another kind of question, if you're planning for your retirement, is, let's say that if we need, say, $30,000 after 20 years, and we have an interest rate of 2% per year, what do we need to invest? Well, what we're going to say here is the amount after time t is going to be the initial amount times e to the 1 over 50 t. But we want to say that after 20 years, we've got $30,000. So I want $30,000 to be equal to the initial investment times e to the 1 over 50 times 20. So this means that I'm going to have 30,000 divided by e to the 2/5 is equal to my initial investment. And then you can just plug this into a calculator and you can see, what does this come out to be? What do I need to invest today at 2% interest if I want 30,000 after 20 years? 30,000 is obviously not going to be enough to retire on, but like, these are the kinds of questions that you can answer. I'm just doing this with made up numbers to sort of show you how you would answer these questions. So there we go, a nice example of a very relevant question. Now, you'll notice that in some sense, so far, most of what we've done today really hasn't involved calculus. Well, that's true on one level. But where do these formulas come from? Why do we have these exponential decay formulas? Or in this case, when we have p e to the rt, this is known as exponential growth. Well, they come from functions whose rates of change are proportional to their value. So they really do come from calculus. We are using calculus here to say, that is where this scenario is coming from. That's why these equations work. Now, working with the equations directly, we often don't really need to use calculus. No, that's true. But the whole reason why we know these things have the properties we want them to is because we understand something about calculus now. Okay, so let's take a look at one more sort of area where we can apply exponential growth, and that is to populations that are increasing without limit. So population growth without constraints. What do we mean by without constraints? Well, in the real world, if you have a population of animals, there's a limited amount of resources. So like eventually there's too many animals for the amount of resources there are. And then the animals start to die off faster because not all of them can eat enough and things like this. There's competition for food and so on. But if there's an effectively unlimited amount of food, in other words, if we don't have to worry about animals competing for food, then they're going to reproduce at a certain rate and they're going to die off of old age and predation at a certain rate. So overall, their population rate of change is just going to be proportional to their population. So once again, we can say P prime is going to be equal to some growth rate times P. That means the population after time T is the initial population times e to the RT. And by the way, one other thing that I didn't really mention here, this is why E becomes so important, because E is naturally the base that you end up with when you're dealing with growth rates or decay rates. It just shows up naturally in the solution to these kinds of questions. But these kinds of questions are exactly the kinds of questions that show up all over the place in the real world. I mean, we're just looking at a few different examples here, but this kind of stuff shows up in all kinds of other applications. We're going to mention a psychology application in a minute, in fact, 2 psychology applications. But so here's the population growth thing. And so one thing that we could ask then maybe is we could say, well, let's say that 200 rabbits were let loose in 1990, and in 2000 there were 4,000 rabbits, and we want to know what is the population growth rate, assuming, of course, that there are no constraints on the population growth. Again, if you have to deal with something like, eventually they're going to have to compete for food and things, well, then you have to modify your conditions slightly. Because this is not a failure of the exponential function. It's a failure of the equation that you're asking it to solve. To say that the population is proportional to its growth rate alone is going to mean that it's growing without constraints. So the no constraints model tells us, in that case, the population growth rate should be proportional to the population. If you do have some limitations, like if this is a small island, so they're going to very quickly start running out of food, well, then the model is different, the equation is different, and the formula becomes different as a consequence. Okay, so what we can say is that P of t is going to equal 200 e to the RT, where t is in years after 1990. Because year 0 is the release of the rabbits. That is when we released them. Well, 10 years later, we have 4,000 rabbits. So 4,000 equals 200 e to the r times 10. This means, why am I having trouble doing this in my head? This means 20 is equal to e to the 10r. So log 20 is equal to 10r. That means r is equal to the log of 20 divided by 10. And there we go. So it's exactly the same as working the previous types of problems. In fact, you'll notice that all of these different types of problems, from all these different areas, the mathematics behind them is pretty much identical. And this is not surprising because they have exactly the same mathematical models. They are all coming from this differential equation that says the derivative of a function is equal to some constant times the function. Well, if two different things, even if they come from totally different fields and describe totally different situations, if they both have that same description mathematically, then the math behind them will be identical. And this is where mathematics, people don't really think about this, but this is where mathematics really helps us to see connections in the real world that you might not otherwise recognize. Because it shows us that there's patterns that come to us repeatedly in nature. There's not just like, oh, these two fields are totally separate. You know, what is the relationship between nuclear physics and studying populations of rabbits? Initially, it seems like these should have no similarity whatsoever. But it actually turns out the mathematics describing them is virtually identical. So really, these two situations are very analogous to one another, very comparable, even though they don't seem like it ahead of time. And mathematics has the power to show us those underlying connections that are not really obvious at first glance when you look at this stuff. Okay, now I told you I was going to give you some psychology examples as well here, and that's what I'd like to talk about next. So where does this show up in psychology? Well, part of it comes in from learning and memory. It turns out that the way that people remember things, or rather, the rate at which you forget learned material, follows an exponential decay curve. So it turns out that you can effectively model the decay, and this is a slightly different situation. The formula describing it does become slightly different, but it turns out that the amount of remembered material after time t is going to be equal to the learned material minus some maximally forgotten material times e to the minus RT. So L is the amount that you have learned, and F is going to be the maximum that you forget. So usually people don't forget things completely. You still remember at least some of a certain material. But it turns out that the rate at which you go from everything you ever knew down to the most you will remember in the very long term follows an exponential decay curve. Another one that comes in, and this is a very interesting one, it turns out This has to do, it's not just psychology, it's also like physiology. So let's suppose that we want to talk about the feeling of a sensation. How intense is a sensation? Like how intense is a sound? Or how intense is the feeling of somebody pressing on your arm, okay? You can think of other examples too. Well, it turns out that the rate at which the sensation changes, or I'm sorry, let me rephrase that because I'm saying this backwards, and so this is not my area, but it's a really interesting thing. It turns out that the amount of stimulus, which we will denote as ST, per change in sensation, which I will denote as SE, is proportional to the amount of the stimulus that you have now. So this is an interesting thing because what it's telling me is that if I want to increase my sensation by a certain amount, I have to really increase the sensation. So what it turns out to be is that the felt sensation is going to be equal to some constant A times the natural log of the stimulus. It follows a logarithmic pattern. So what this means is, here's a good example of this. Think about frequencies in sound. If you double the frequency, we hear the sound go up by exactly 1 octave. But if you take the frequency up by a factor of 4, we hear it only go up by 2 octaves. It doesn't follow a thing where the same increase in frequency is perceived to have the same difference in sound quality. The sound quality follows a logarithmic pattern. In this case, it's most natural to write it in log base 2 rather than with a natural log, but it turns out that you can fix that up with these formulas. Another example is how loud something sounds. So it turns out that the perceived loudness follows a logarithmic curve with respect to the amount of power in the sound waves. So if you want to increase the loudness, you have to really start jacking up the power quite a bit as it gets louder and louder. And this is why certain things are measured in what are called, like loudness is measured in decibels. Well, decibels actually follow a logarithmic scale, and you can look in your book for more details of this, but that is why we measure loudness in a logarithmic scale. It's because our ears actually perceive sound on a logarithmic scale, which we don't realize that normally. We really have no idea that that's going on. But all the time, we are dealing with a logarithmic scale. And the same sort of thing has been found to go with sensations and other types of things like this. Now, I forget the name of the scientist who's came up with this law, but it's in your textbook. So you can look up the name of the person for whom this law is named. Although you always got to be a little bit careful because sometimes the person for whom it's named isn't necessarily the person who always discovered it. Sometimes it's like some poor graduate student discovered it and their advisor got the credit for it in the history books or something. Or sometimes it's one person discovered it but never really did much with it, and then somebody else came along and widely publicized it. And maybe they didn't even try to take credit for it. Like maybe they said, no, I didn't do this. It was this guy over here who did it. But everybody looks at it and says, oh yeah, it's what this guy's been publicizing. And they name it after the second person instead of after the first. So anyway, you can look up what that is. But the point is that we measure a lot of things with sensations using one of these logarithmic scales. And the reason is because the amount of stimulus it requires to change a sensation follows an exponential pattern. So when we flip that around and look for the for the sensation as a function of the stimulus, it becomes a log function. All right, so that sort of takes care of some of our basic examples of where these things show up. Next time, we are going to take a quick glance at some slightly more complicated models, like what do you do if you have a population cap? Like, what if there is some sort of constraint on how big a population can grow? And other sorts of things like this. We'll also look at things like Newton's law of cooling and different things of that nature, which also can be described with exponential functions, but maybe in a slightly more complicated way.